So we continue with the afternoon session, and our first speaker is Thomas Yahl, who is going to talk to us about Galois groups of purely lacunary polynomial systems.
Cool. Well, thank you. So am I audible to everyone also? Is that good? Okay. Well, I'm glad to talk with you guys about this today, mostly because this is very Frank related. So this is the first project that Frank ever gave me as a graduate student. So I approached him and asked him what things he was thinking about, what he was working on. And he said, oh, I have this idea. We could probably solve this over a summer. And it's now 6 or 7 years later. And so now we at least have some results that we can report. And I'm here to tell you what those are. So there's a lot of words in this title and a lot of words that people maybe are not familiar with. So luckily, we're going to define all of them. The first one being Galois groups. I think this is something that scares a lot of people when they see it. They think of field extensions and automorphisms and normal closures and all this stuff. I'm also glad to announce that there's 0 of that in this talk. There's no field extensions. All of that has been removed. This is all geometry. We're staying away from that side of it. So what is a Galois group in that case then if we're going to do this all geometrically? So we need to set up, we'll look at Galois groups of enumerative problems. And so to me, an enumerative problem has 3 pieces of information, 3 data. So we have some space of parameters. So my sort of canonical example in my head of an enumerative problem is the lines on a smooth cubic surface. So the parameter space in this case would be the moduli space of smooth cubic surfaces, or if you prefer, just cubic polynomials and 4 variables, homogeneous. We have a solution space, which in this case would be the lines that lie on said smooth cubic surface. So that'd be some Grassmannian of lines in P3. And we have this incident space, which is all pairs of cubic surfaces and lines that would be incident with them. Cubic surface. Thank you. So this one actually does have 27 lines on it, and I have about 30 of these at home just like it, thanks to Frank. Yeah, well, here you go. Okay, but for me, this is the setup of an enumerative problem. We just have these 3 pieces of information, and then with these 3 pieces of information, we have a projection from our incident space to our space of parameters. And the reason that we care about this map is that this map tells us about the solutions. So if you look at the fiber, if you choose a set of parameters, so this is a choice of cubic surface, like the one being passed around, then the fiber of this map is all lines that are incident with it. So this would be all lines that lie on that surface. And so because we work in the wonderful realm of algebraic geometry, this map restricts to a smooth covering space, in this case a 27 sheeted covering space, because we have these 27 lines. So this is my viewpoint of enumerative problems. This is our setup. This is what we want to get to at some point. Because if we have an enumerative problem, if we have this exact scenario, we can define a Galois group. And so to me, a Galois group of an enumerative problem is just the monodromy group of that covering space. And so if you haven't been in a topology class for however many years or have never seen monodromy groups in your life, so a monodromy group is we choose some base point in our space of parameters. So again, this is a choice of, for example, a cubic surface. And so the fiber, again, would be all these lines that are lying on this cubic surface. And what we do is we look at directed loops based at that point in our parameter space. And that loop, again, is some contorting this cubic surface. You're changing the coefficients of your polynomial. And eventually, we're coming back to the polynomial that we started with. So we just have the original cubic surface. And what's happening up above is if you choose any line, you can follow that line as you twist and distort that cubic surface. And as you come back to where you started, that line might be in a different position from where it started. And so as you move around in your space of parameters, these lines all mingle and mix and match. And as you go around in loops, you get some permutation. And so the set of all permutations that you get in that way is the monodromy group. And so we'll call that a Galois group. Okay, and so these are called Galois groups because Jordan initially studied these Galois groups, but he studied them all algebraically as actual Galois groups. So if you do like the algebra, you do like field extension and all that, there is an algebraic view of all of this. So everything that I say in this talk, you can turn into algebra and fields. We're not going to do any of that. So the big lingering question about Galois groups, even if you see this, there's the lingering question of why do you care? So most people, I think, would argue that Galois groups are not something that they use in their day-to-day life or don't want to use in their day-to-day life. And to quote Frank, you might not care about Galois groups, but your problem does. So there's tons of examples where people use these Galois groups and use this structure. So the big one that I think most people are familiar with is solvability by radicals. If your Galois group is solvable, you can compute solutions in radicals. And this is something that people actually do use in applications. So there are problems in chemistry where they have systems of differential equations, and maybe they set some rate constants equal to 0 to see what happens in the long term. So then they have these mixes of differential equations and algebraic equations. And to get back to differential equations, they want to be able to solve these equations explicitly in terms of radicals to get back to differential equations. Even if you don't know the whole Galois group, even if you can't solve by radicals, even just partial knowledge of the Galois group can help you reduce some computation to simplify your problem. So Maggie, wherever Maggie may be, has done this, for example, for computer vision problems. This is something that is super nice. If you have any knowledge of the Galois group, you can use that knowledge to find some way to decompose your problem. So this is highly, highly useful, I gotta say. Otherwise, this has come up, for example, for trace tests. Trace tests are utterly important for all sorts of numerical computations. So this is something that has come up, for example, with the sparse trace test. And if that's not enough for you, of course, Galois groups are just interesting objects studied by all sorts of famous mathematicians. And if it's good enough for them, it's good enough for me. And hopefully it's good enough for you. So just to put this in context now, we want to look at Galois groups of sparse polynomial systems. And so for context for this is that this is the context that I was provided. But it turns out this is still relevant today. So Estrov was the first to look at Galois groups of sparse polynomial systems to see which of them are solvable by radicals. And so Frank, Taylor, Jose, and I wrote some code to utilize the structure of Galois groups to help compute solutions to them, just based off of partial knowledge of what the Galois group is and its structure. And then very recently, Taylor and Michael Burr utilized Galois groups of sparse systems when they're creating a sparse trace test, like I said before. So Galois groups, awesome. That's my whole spiel today is that Galois groups are great. You should love them. But also that sparse polynomial systems are relevant and their Galois groups are interesting. That's sort of the baseline for today. So to actually get into some of this math now, so a sparse polynomial system, that's our main object that we want to look at. These are just systems where we're going to restrict the monomials that we allow to appear in each of our equations. So we're going to allow Laurent monomials, we're allowed negative exponents. So we have an exponent vector for any given monomials. Monomial, again, is just a product of powers of our variables. We'll have n variables in this case. And so if you choose a set a and z to the n, so this is going to be our way of choosing the monomials that we allow to appear in a polynomial. We'll call that a set of support, or we'll call that a support. And so a polynomial f of support a is just a linear combination of those monomials, and the coefficients will allow to be complex numbers. So we have complex systems, or complex polynomials. And so now a sparse system is we'll have a collection of n of these finite subsets of z to the n. And so these will give us systems f1 through fn, where we allow each fi to have support ai. So we're in some sense literally looking at our polynomials and saying we're only allowing these monomials to appear in each of these equations. Okay, so quick example. This will be our running example throughout the entire talk. We'll see this like 7 times or something. So we have these supports b dot. Why I've called them b dot instead of a dot here will be relevant later on. But we have these supports b dot. We have 2 of them in Z2. So we'll have 2 polynomials and 2 variables. We'll always work with these square systems. In this case, these are both set of 3 points in the plane. So we'll have 3 monomials in each of our equations corresponding to 1 xy squared, x squared, y squared. And this one will be x, xy, and y squared. And there's no typos, so that's good. Okay, so that's kind of where we want to start off with, just polynomials. We're choosing the supports, and sort of the canonical theorem that everyone learns about when they learn about sparse systems is the famous BKK theorem. So if you have, say, n convex sets in Rn, the mixed volume is some measure of the size of these convex bodies. And I will not say any more than that about what mixed volume is. If you know what mixed volume is, great. And if you don't, we don't need anything more for today, and so I won't tell you anymore. And so we'll say that the mixed volume of our supports A dot is just the mixed volume of the convex halls of those supports. And the wonderful famous BKK theorem says that if you have a system of support A dot, meaning you've chosen the monomials to appear in that form, then it has at most mixed volume A dot smooth isolated zeros in C star to the n. And this bound is generically sharp. So if you choose general coefficients, you have exactly this many zeros. Okay, And so again, mixed volume, if you've never seen it before, I highly recommend you look at several books on this. There are many great ways to compute it. There are many softwares to compute it as well. And so for our running example that we saw before, if you plug this into Macaulay 2, for example, or whatever your favorite mathematical software is, it'll spit out that the mixed volume of these supports B dot is 6. So there are 6 solutions here for general coefficients C1 through C6. Great. So now that we have kind of the setup for an enumerative problem, we can actually define the object that we want to study because we have a space of parameters. And so you should think of this as the space of polynomials of support A dot, or if you want to think of this as an affine space, you can think of this as some list of the coefficients of your system. We have a solution space. We're looking at solutions or zeros in C star to the n. And we have this incident space of our systems and zeros of that corresponding system. Okay, and so this incident space projects down to our space of parameters, PA. And from the BKK theorem, this restricts to a mixed volume to 1 sheeted covering space over some Zariski open set, so over some dense open path connected set. And like we said before, if we have an enumerative problem where we have these finitely many zeros like this, we can define the Galois group, which is just a monodromy group of this map here, this projection. Okay, and again, if you love numerical software, which you should, this is something that you can do numerically through various software. So there's Bertini, there's homotopy continuation.jl, there's numerical algebraic geometry in Macaulay 2. There's all of these softwares that will actually do this numerical path tracking for you to actually lift these paths. And so you can actually numerically approximate what these Galois groups should be. And so for our, our test system, our running example that we have, if you go into Macaulay 2 and you change these coefficients and see how these roots permute, you actually quickly find that you can get all possible permutations. So now there's a question of why is this symmetric group? And there's this idea instituted by Jordan that these Galois groups should be as large as possible, as large as the problem permits. So sort of the typical behavior that you should expect when you're computing a Galois group is that it's the symmetric group. So that's sort of, in some sense, the boring thing that happens is that you get the symmetric group and you say, okay, there's no additional structure to my problem. That being said, that's not always the case. We know there are problems in mathematics that are highly structured where many interesting things happen. And it turns out for a lot of sparse polynomial systems, there are more interesting things that happen. So there are relations among the zeros, and so that constrains the Galois group in some way. And so if you do have this additional structure, you have small Galois groups. So we end up with just two open problems then. So the first one is the inverse Galois problem, and so this is sort of a famous problem, but we can phrase this in terms of sparse polynomial systems. We can ask, what are the groups that appear as the Galois group of a sparse system? And this is a very, very, very hard problem. There have been a couple conjectures along the way, and every single one of these conjectures has just been wrong. I will say if you know of a conjecture, I will say that it's very likely somewhat uninformed. There's not really a good guess of what the answer for this problem is, I'll say. And another related and very difficult problem is if I give you a set of supports, how do you actually determine what this Galois group is? And so there's been partial progress in this front. So Estra was one of the first people to study these systems. He was the first to study the Galois groups of these systems. And he was actually able to determine exactly which supports give you the symmetric group for the Galois group. So to understand this, we need two special classes of supports, which you might be able to guess from the things on the board over there. So these are very informal definitions. If you want formal definitions, you should read some papers. Otherwise, if we have a set of supports, we'll call it lacunary. If any system of that support has been precomposed by some monomial map. So in this example over here, we have the system G. You can say the support here is just the set 0, 1, 2 for the monomials 1x, x squared. And the system F down here would have support 1, 3, 6, and it has been precomposed with this map x goes to x cubed. And so in some sense, this lacunary structure, you're doing some operation just on the monomials that appear, and this, So this is going to give us some sort of structure on the zeros of F, some constraint, and this will constrain the Galois group in some special way. And the other structure is this triangular structure, which will say a support is triangular if any system of that support has some proper non-trivial subsystem. Proper and non-trivial here, meaning it's not the empty subsystem and not the entire system itself. So we actually do have a proper subsystem. And Estrov's theorem basically says that these are the only structures that can impede your Galois group in some sense. So Estrov's theorem is just that if your support A dot is not lacunary and it's not triangular, then your Galois group is the entire symmetric group. And so I will say modulo trivialities, there's a converse to this statement. So if you have a Galois group which is the symmetric group, it's either some trivial case or your supports are lacunary or triangular. Okay, and so as nice as Estrov's theorem is, the proof is not very exciting, I'll say. So if you want to prove that a Galois group is the symmetric group, which again is sort of this typical behavior, there is a very standard argument to do this. So the first step of this argument is to look at a small loop that you take around the discriminant locus. So you're looking at where 2 points have come together. And so you know if you slightly perturb that system, that singular point that you hope has multiplicity 2 is now split into 2 points. And if you take a small loop around the discriminant, then these 2 points should just transpose one another. Okay. And the second step is to show that the Galois group is 2-transitive, and there are standard arguments to do this by looking at fiber powers and the irreducibility of certain components, or of certain subvarieties. And once you have these two properties, you immediately have that these two properties generate the whole Galois, or the whole symmetric group. So your Galois group is the symmetric group in that case. So this is exactly what Esterov does for these sparse polynomial systems, and we get the result. Hurrah. So beyond this, though, there's only very few partial results on what the Galois group looks like in these other structured cases. So we're going to look at what happens when our supports A dot are lacunary. We want to know what happens to the Galois group. Can we say anything meaningful, or say what the Galois group is? Okay, so this is where we start to do a deep dive. This is kind of, we've hit sort of the background point. So we've said this already, but a system is lacunary, or a set of supports is lacunary, if there's another set of supports B dot and a monomial map, so that any system of support A dot has been precomposed by that monomial map phi with some system from the support B dot. And these systems have the exact same coefficients, and an example is worth 1,000 words in this case. So again, this would have support 0, 1, 2. This has support 0, 3, 6. And this monomial map is taking, the system F is the composition of G with that monomial map. And these polynomials have the exact same coefficients. The only difference is that monomial map is changing the monomials that appear in each of these equations. Okay. And so the support B dot, which in this case, again, is that 0, 1, 2, we'll call that a reduced support for A dot. And then this is where we start to see some of the structure come into play here. So this monomial map is a multiplicative map. So a monomial is a multiplicative character, and a monomial map is a map whose coordinate functions are all monomials. So we actually have a group homomorphism. And if this map is surjective and not invertible, then this kernel here is a finite group. And it's actually a group of units, which are products and quotients of roots of unity. And this finite group acts on the zeros of F. Right? So if you have a 0 of F and you multiply by something in this kernel, that monomial map just kills that element of that kernel, and so you just have this group action by this kernel. So what this means is that we can partition the zeros of F. So the zeros of F are partitioned into orbits of this K action, or partitioned into K orbits. And so the number of these orbits is equal to the mixed volume of our base system, and the size of them is equal to the size of that kernel. And so again, you can see this sort of by example. So in this case, our system F, if we wanted to actually solve for the zeros of F, well, we would solve this quadratic G, and then we would extract cube roots. So we would end up with 2 roots of this system G, which would correspond to these 2 blocks. And then in each of those blocks, we would get cube roots of the system, of the zeros of G. So the structure of the zeros comes nicely just from the description of lacunary systems. And then what's really nice is that this Galois group action on the zeros of F actually preserve this partition, because they commute with the action of K on the zeros also. So the Galois group is actually imprimitive. There's some non-trivial partition of the zeros that's preserved, and we'll call these orbits blocks of imprimitivity, because these are the partition that's actually preserved by that Galois group. So automatically, just from this description, you can say that this Galois group is not equal to the symmetric group because the symmetric group would not preserve any such partition. So the Galois group being imprimitive here is some constraint that this Galois group is not equal to the symmetric group no matter what you do. And so there's another group that acts on this partition. So there's this wreath product. And so more formally, wreath products are some semi-direct product of these groups. So we'll think of this wreath product as all of the permutations that permute these blocks freely. So we have this, in this case, S3. You could permute these blocks however you want. And then in each of these individual blocks, we'll allow some action of K inside that block. And so because each of these blocks is some K orbit, you can actually act in that block by K, and everything stays in that block. And so a very quick result is that the Galois group is a subgroup of this wreath product. And so we said before that the Galois group should be as large as humanly possible given the constraints of the problem. We know that the Galois group in this case is imprimitive, and this is sort of the next largest thing that it could be. So it's very natural to guess or assume, okay, maybe that the Galois group should be equal to this wreath product. And in a lot of cases, it is equal to this expected wreath product, but that's not necessarily always the case. So there's some additional structure that can impede the Galois group, and that structure is very hard to detect. So for our running example now, we were using B dots that whole time. We finally introduced our A dot supports. So our supports A dot are going to be obtained from our support B dot by just scaling the first coordinate by 2. So this has the effect of just precomposing our system of support B dot by the monomial map xy goes to x squared y. So it's a very simple operation that we've done to our supports, but it does a large effect on the Galois group. So the kernel of this monomial map is pretty simple. We just have 1, 1 and negative 1, 1. We know our reduced support B dot had mixed volume 6. So we have 6 orbits of size 2 for the zeros of a system of support A dot. And so the Galois group is a subgroup of this wreath product, and it's actually a proper subgroup of index 2. And so this is where the question lies, why is this index 2? What is the additional structure, or what is the additional constraint? What relation are there among the zeros of this system that constrain the Galois group in this way? And this is one of my favorite examples, because if you look at a lot of examples, for example, in the literature, there's an example that someone has where it's a proper subgroup, and the supports they give are very symmetric. And so you might say, okay, maybe this comes from the symmetry of the supports in some way. These supports have very little to no symmetry. It is not apparent in any way what the support is, or what this additional structure is. So that's what we're here to talk about today, is what this hidden extra structure is that's impeding this Galois group. So the right set of supports to look at aren't just lacunary supports, but these purely lacunary supports. And this is our way of just isolating this lacunary structure. So a purely lacunary support is one that's lacunary and not triangular. We're just removing any of this additional structure that can impede things. And so alternatively, a set of supports is purely lacunary if there's a reduced support B dot where the Galois group of B dot is a symmetric group, modulo trivialities, minus trivial cases. And so our support that we were looking at on the previous page is actually purely lacunary, because we know our reduced support B dot had symmetric group as its Galois group. So what can we do with these purely lacunary systems? What actually helps us and allows us to actually determine what the structure is? And so we end up kind of doing the standard argument to figure out what the Galois group is. And then once we know what the Galois group is, then we can figure out what this structure is. So we kind of reverse engineer the problem a little bit. And so to figure out what the Galois group is first, like I said, we follow this standard argument, but there are obvious holes in using the standard argument to compute the Galois group here. So before we said if we take a small loop around the discriminant, we should get a simple transposition because we get a singular zero of multiplicity 2. With lacunary systems, we no longer have a single multiple zero. We now have many of them. So now a small loop around the discriminant will not give you a simple transposition, period. And because our Galois group is imprimitive, it is not too transitive. These are contradictory properties that cannot be both. And so the question is, how do we adapt this standard argument to tell us something about lacunary systems? So I will say that it turns out this first one is actually very easy to solve. So instead of having this one simple zero that splits into 2, you get one simple transposition. we now get several transpositions. And so if you have a purely lacunary system, a small loop around the discriminant now actually just gives you a simple transposition of your blocks. Okay, so it works out almost exactly how you would expect that it should. And there's this small caveat here that we need to take a loop around this b dot discriminant. So because these polynomials have the same support, you can identify these parameter spaces, and you can still take a loop around the discriminant in the reduced support. But if you look at the discriminant of a dot, there might be more components than you'd expect there to be. And so we need to take a loop around this b dot discriminant so that we can force these two blocks to actually swap. So there are more things that can happen if you look at loops around other components of the discriminant. But it's specifically around these components, you get a simple transposition of blocks. So that problem is an easy fix. The harder problem is what do we do about two transitivity because our group isn't primitive. These are contradictory notions. We can't do anything about this. So we come up with a new notion of transitivity for imprimitive groups. So we say an imprimitive group acting on a set S, imprimitive here meaning again that we have some partition of the set S into blocks like this. We'll say that it is k block transitive if for any set of k points from distinct blocks and any other set of k points from distinct blocks, there's some element of G that maps the first set of points to the second set of points. And so this is directly analogous to just transitivity in general. So if you have a group that's two transitive, you take any two distinct points, show that you can map the first set to the second set. This is the exact same property, except now we have the constraint that these points all belong to distinct blocks. Okay? Yeah.
So this is a block transitive with respect to these minimal blocks.
Yes. So not necessarily minimal, just any partition of the roots that you have, or any partition of the set S that you have.
I was going to ask on the last slide, maybe if you just run through the version of block transitivity, but if you restrict to, say, small loops that perform a simple transposition of the blue block and the red block, you get all possible bypass.
So yes, you do get all possible permutations of these blocks. I should have also mentioned that this block swap this transposition of blocks also may require reordering the zeros. That way you actually do have just the swap. Otherwise you might have that these are misordered or something. So you do have to be a little bit careful. But yes, I will say that you do get all possible permutations of the blocks themselves, but more things might happen inside the blocks.
Yeah, so the answer to this question is no.
Yeah.
Oh, maybe.
But yes, if you want to look at transpositions that switch the blue block with the red block,
Mhm.
you just consider all the different groups that switch the blue block and the red block. You
Ah.
in fact give you 4 factorial.
Gotcha. That.
I guess what you're saying is you take such transposition and you can use that to identify the different blocks.
Yeah.
And go.
Well, that's unnecessary, but yes.
But you're not really doing that.
Yeah. Okay. So as you might guess, this generalized notion of transitivity for imprimitive groups, we've defined this. You would hope that our Galois groups are two-block transitive, and that is exactly the case. So if you have a purely lacunary set of supports, if you look at the partition induced by blocks that we have from this group action, our Galois group in that case is two-block transitive. Okay, all right. And so it turns out that sort of the standard idea for looking at transitivity works also for lacunary systems. So normally you would look at a fiber square and show that this fiber square has two components. In this case now we look at the fiber square, but instead of showing that it has two components, we look at a certain subvariety and show that that's irreducible.
So question, I mean, is this your notion or is k-block transitivity in the literature for permutation groups?
So I looked quite a bit and I couldn't find anything on this. No one seems to look at notions of transitivity for imprimitive groups, but it may exist and I just couldn't have found it. So as far as I'm aware, this is a new notion.
There are a couple, I mean, the literature, the recent literature on like permutation groups is interested in infinite permutation groups. So you have to go back a while to find papers, books written like the 1950s or earlier that
Okay. Yeah, so maybe I'll look a little bit harder, look a little bit farther back, but as far as I'm aware, this is new. Okay, so in the original case, once we had a simple transposition and two transitivity, we had the full symmetric group, we are done. We have this question now if we have a a transposition of our blocks, and we have two block transitivity. There's this question of what does this give us for the Galois group? And so you can kind of play with things a little bit, and you can get the result, but the result is, it's not very insightful to play with these properties to try to build things. So the punchline is probably more important than how to get to the punchline, I'll say. But we have, so we said that the wreath product is all permutations of these blocks, and we're allowed a k action in each of these blocks. So we'll represent an element of this wreath product by a tuple like this, where the sigma is the permutation of these m blocks. And this k1 through km are just the permutation, or just the elements of k that we're allowing to act in each block individually. And so we define this map from the wreath product to k itself by just taking the product of all of these k's. And so we're going to look at the kernel of this map. These, in some sense, are the permutations that are balanced, where you're sort of balancing how you're acting in each of these blocks overall. And so the result is that if you have an impermuted group which is two block transitive and contains a block transposition like this, then it contains the kernel of this map. So we have all of these sort of balanced permutations. So combining everything, we now have that if we have a purely lacunary set of supports, then our Galois group contains this kernel of this map. And what that also means, because it contains the kernel of this map, that the Galois group is identified with a subgroup of K. In particular, the Galois group is equal to sigma inverse of some subgroup of K. So we now have at least a result that tells us these are what, or this is the Galois group. But of course, as you can tell from all this, there's a lot of lingering questions that come out of it. The first one being, do all groups of this form actually appear as the Galois group of some sparse lacunary system? And I don't have an answer to this. So my guess is no. From numerical experimentation, it looks like there's some divisibility constraint that always needs to hold. This is something that should not be hard to prove, but it does rely on a product of powers of facial resultants and some polytope business, and it's not immediate why this should work. So this is something that I think if I talk to the right person, this should be very easy to figure out. But at the moment, this is something that I don't know. And then the second part is now, if we have a set of pure lacunary supports, A dot, how do you actually determine this subgroup H and actually figure out what this Galois group is? And it turns out this is also a problem that is not very easy, but there's some geometric realization of that map sigma, and from that geometric realization, we can say exactly what that subgroup is. Okay, and so this is where things take a bit of a turn. So everything we've looked at so far has been somewhat localized. We've looked at loops around discriminants. Things take kind of a more global turn to figure out what this subgroup H is. So our goal at this point is to actually find this subgroup H, be able to give some clarity on how do we actually determine this. So this next slide is a little bit of a flashbang, I think, because it's such a left turn. But we're going to define some new variety. We'll call it JA dot. Okay, so for those of you that are familiar with some of this, how we look at these Galois groups, this is maybe not something new, but for people that have never seen this, this is maybe a bit scary. So we're going to look at the variety of systems and a list of all of the solutions. So this, and some people might call this a top fiber power of this map.
So those are distinct.
Yes. Well, in this variety, not necessarily, but I would like them to be distinct. Yeah. So we're going to let this JA dot be any component of this variety that's, that maps dominantly to our space of parameters and that is not contained in the diagonal. So we're assuming that each of these xij's are distinct for different I and j. So this is kind of a scary variety. This variety actually contains all the information about our problem, all the information about the Galois theory, and it's very hard to compute. If you try to put this into a computer, your computer will very likely be upset at you and not spit out anything meaningful. But this variety is sort of the key to figuring out what this group H is. And so we're going to look at the deck transformations of this variety. So these again, so these will be the birational automorphisms of this variety that preserve the fibers of this map. And so the way that you should think about this are these are going to be maps of this variety that preserve, if you have a given system F, they preserve the zeros of F, sure. And so the way that this works is these are really just going to reorder the zeros of F. And so you can show that these deck transformations, if you have a system F, they actually act on the zeros of your system by just permuting them. And so we now have two groups that act on the zeros of a system F. We have this group of deck transformations of this variety, and we have the monodromy group. and they turn out to be equal. So the Galois group that we defined as the monodromy group of this covering space is actually equal to the deck transformations of this sort of odd variety.
Are they actually, they're actual maps?
Yeah. So the reason we need this variety JA dot is just so we can define this new map, this geometric realization of sigma. And this map is also a bit odd at first. So we're going to define this map from JA dot to the space of parameters cross S, or solution space. And the map will just keep this F the same. And we're going to take a certain product of the zeros of our system F. And so this certain product is we're just going to take one zero from each of our blocks and multiply those together. That's a very odd thing to do. Instead of looking at sort of the product of all the zeros, we just want a product of just one zero from each block. Okay? And it turns out that the group of deck transformations of that JA dot that preserve fibers of this map, so that'll be a subgroup of the deck transformations that we looked at before, so it'll be a subgroup of the Galois group, that's actually equal to the kernel of that map sigma. So this is a bit odd. So it takes a little bit of thinking to understand sort of how this map works. But if you were to act on these zeros by multiplying by some action of k, so again, these are roots of unity, when you look at the product, you basically have just the product of those values of k. And so to preserve that product of those roots would be to have sort of this balanced permutation. So it's a little bit hairy, but as a quick corollary to this, once we have this understanding, then...
So you're taking a transversal to the blocks?
Yeah.
Okay. Choose a transversal, you know the index, it's just 5.
Right. Okay, and then once we have this information about these deck transformations, we can say that this subgroup H is a subgroup of K, and so, right, I should say that, well, okay. We'll say the subgroup H we can identify with the deck transformations of the image of that map that preserve the system, basically. So that's a lot. Like I said, it's sort of a left turn from what we were doing before to actually identify this subgroup H. We at least have some description of it. That's awesome. There's this lingering question now of, does this actually help us? Is this something meaningful that we can actually use to find H if you have an example? And the answer is yes. So this variety image of H has very simple defining equations. You can write these down for small enough examples. So we're going to define a small function first. This is not actually a function, but we'll get to that. So if you have a system of support A dot that has this reduced system G that you've precomposed with some monomial map. So we're going to let this PF be all of the product of the zeros of G. So because these have the same coefficients, this is actually a rational function. It's actually a rational function to C star to the n, so it's okay. Okay, and then this variety image of pi is defined by just these binomial equations. You have this monomial map that we've been working with this whole time, minus P of F. So it sounds easy, right? Binomial equations, we should be able to do this no problem. The real problem with this is finding some expression for this PF. And it turns out that this PF you can write as a product of powers of facial resultants that come from your polytopes of these supports A dot. And so it turns out that's not a particularly easy thing to do if you have large sets of supports. But you can do it for small examples. So I put the coefficients next to the corresponding point in the plane to tell us what coefficients are coming from where. And so for our example support A dot that we've been looking at this whole time, we can actually write down what those equations look like. And so they look like this now. And so you can see there's some funny business happening. So I've also cleared the denominators, so these coefficients out front are from clearing everything. But you'll notice there's some funny business where this first equation here is a difference of squares. So this variety is not irreducible. There are in fact several components. 2 of these components actually map dominantly. There's other components that don't map dominantly. Those are sort of irrelevant. But this variety splits into 2 components, both of which are just defined by simple linear equations in x and y. So these have no deck transformations. There's nothing that can permute these irreducible components. And so our group H in this case is just the trivial subgroup. And so the Galois group in this case is just these bounds permutations. So in hindsight, now the hidden support that's impeding the Galois group from being the full wreath product is just the fact that the product of the zeros of the reduced system is a perfect square. That's really the problem that shows up. And so now the problem is if you give me a general set of supports to actually determine whether or not this is a perfect square, that's something that I don't know how to do without actually explicitly computing this function. And so that's the remaining part to do this, to prove anything more generally, is to say something about this product of powers of facial resultants, which is, I think, combinatorial at some point. And then sort of the typical thing that happens, so instead of scaling everything by 2, if we had chosen to scale everything by 3 instead, so now everything is the exact same that we go through the problem, except now this variety would be defined by the same thing, but with x cubed there. And so now this variety is irreducible. You can plug this in Macaulay 2 if you want. Okay, I lied. It's reducible, but all of the other components are sort of trivial components that don't project dominantly to our space of parameters. They're components that we don't care about. They're superfluous. They're irrelevant components. There's only one component, and on that component, there's this group of roots of unity that act on that variety as deck transformations. And so in that case, this is also our group H. And so we actually get all possible elements of the wreath product. And so the Galois group is the full wreath product in that case. So in other words, in this other case back here, it just so happened that we just so happened to compose with some monomial map x goes to x squared, where this is now a difference of squares, where there's some common factor of these powers. Or in general, if you were to choose random monomial maps, that's very unlikely that these would factor, and you would actually get the full wreath product. But okay, so that's all I've got for you guys. Hope that was informative.
Yeah, there's some actual real field theory in your facial resultants. These course, the components of them are primes that don't, it has to do with whether the primes, the zeros of them are prime ideals in the parameter space, and the question is whether those primes split in certain intermediate extensions. That's what, that's a field theory way of understanding what you're seeing here.
Okay.
Do you have any misinformed conjecture on what it is when triangularity is included?
I knew someone was going to ask it, and I figured it would be you. So yes and no. So I'll say that the triangular case is significantly harder in general because for lacunary structures, you just have this monomial map. That's it. For these triangular structures, you can have one subsystem, you can have two subsystems, you could have subsystems that sort of intersect or overlap in a different subsystem, you can have subsystems in subsystems, the list goes on, and that's just considering just this triangular structure itself. So you could ask sort of what's the base triangular case, where you have a system that just has one subsystem and sort of nothing more. And so for that, Frank and I got some undergrads to run a bunch of code for a summer and see what they came up with. And so for sort of the base, like minimal triangular problem, the Galois group looked to be either like the wreath product that you would expect it to be, or just a product of certain groups. So the product of the corresponding groups here.
Well, I mean, there's this paper of S. Problem Long, and I think they've actually studied the bivariate cases.
Mm-hmm. Yeah, but they end up with a similar lacunary result. Yeah, but even in that case, they end up gearing everything towards the lacunary case in the very end.
And with the triangular case, you can have multiple block systems.
Yes.
But not in the purely lacunary case?
Yeah, it's not in the lacunary case.
Okay.
Can you go back to the slide where you showed us the definitions for lacunary and triangular?
Yeah, they're
I had a question.
Vague. So many slides, so little time. There we go.
Okay. Oh, no, the next slide. Do those bullet points in the standard argument, does each one kind of map onto each assumption, not lacunary and not triangular, or is it more complex than that?
It's more complex than that. So the not lacunary and not triangular is telling you something about the discriminant in this case. So the not lacunary is telling you that you have just one multiple zero. And then this not triangular is telling you something about the components of your discriminant. Specifically that your discriminant is irreducible and that you don't have sort of different things happening for different components.
Thank you.
more questions? Okay, we'll thank Thomas. Okay, we have a break and then